Ah, huh. All right, yes, live and such. Morning. Ew. Probably a bad idea doing this whole morning thing at all. But anyway, so I figure I would. So the room link is below somewhere, and so if somebody's got some conversation about physics, okay. Physics. All right, yes, fine. Ah, that's me. So I have to pause that. Probably a bad idea. One slight flaw in the plan. Yes, okay. I did post a link before I opened the room, so at least I am learning the curve of the learning. Yeah. And so, yes, curve, that was one of the first things I did think of was the forces. Generally speaking, are created in a curved kind of idea, like acceleration. You don't automatically accelerate a whole bunch. You accelerate and accelerate, then you're getting the peaks acceleration, then you decelerate as something decelerates you. You know, it's never exactly all the way on, all the way off, and nothing else. So that's sort of important in the whole idea of force conveyance. You know, once you turn into an electric or a magnetic force, your velocity or your acceleration, it's only effective. Uh, at first, it takes a while to get to somebody, like light. So once it leaves you, it's not necessarily getting anywhere instantly. So sometimes you can't take it back, so to speak. So, but it's also that you're giving it in a blob where it's more at the beginning. I mean, you know, less in the beginning and then more and then less at the end. So it always does have that curve to it. Um, Force creation, we'll call that. C radiation, and that forces are created by acceleration. And velocity has little or nothing to do with it. As funny as that sounds, right? Yes. Velocity is just the maintenance of a condition, and once you have the condition, you're not making no more forces. Even though you're going fast, it just doesn't matter because you're done making force. You only make force while you accelerate. And that's the consequence of acceleration. So if I was to explain that, do a physics lecture, you know, they often will start off with the history, okay, and say, okay, well, you got Galileo and you got Newton, and then train wreck. Okay, that's how I would describe everything after that. Is just train wreck. Okay, logical train wreck, where, you know, back in Newton's time, say they just didn't, you know, or even Galileo, they had to devise really simple experiments and crude mechanisms to do things, and they were just kind of, you know, there was no room for. I mean, you can't imagine that Newton would do something like invent dark matter or come up with some kind of gimmick. Even the Huygens thing, though, Huygens is pretty old. I don't remember exactly how old, but I think it's Newton's time. You know, this idea, and I don't know exactly what Newton thought of that gimmick. You know, this idea. Let's just pretend. Okay, waves create little wavelets. You know, and we'll make that the truth because it's unimaginable. You can't test it. You can't see it. It's all invisible, so we can make up an invisible kind of a god. And I guess I'm just saying that I don't think these guys were looking for gods. They weren't looking for unicorn answers. They were looking for some kind of physical, hard, you know, some real handle on it. Not some real picture of the physical universe, not some unimaginable description. Unimaginable in the sense that it doesn't have any. You just can't draw a picture of it. You can't model it rationally. Uh, so I guess I would say that there is a dividing line in terms of what physics allowed physics to become, so to speak, what physicists allowed physics to become, in terms of providing explanation. All right, so it's the biggest conflict, I guess the biggest controversy, let's say the biggest controversy is particle versus wave, right? As a elemental function. I'd argue that certainly particles become wavy when you become further and further and further from the source. So it just as this force argument is made that it takes a matter of time to reach the peak of something. You can't change anything instantaneously. You have to change it by changing all the bits, and that takes time. So just that automatically creates that curve. And once you have that curve, you know, then you have something that looks like a wave if you extend it and do this, you know, propagate it through time. You have something that appears like a wave when it's really a frequency. Right. So that would probably be another way of putting this is the notion of a wavelength versus a frequency. So I'd say, you know, we're talking about the same thing. We're just using different conceptual words to describe the same thing. Wavelength and frequency are the same thing, essentially. I mean, a frequency over time dictates a wavelength. A wavelength, you know, one multiplied by time, one divided by time, you know, same exact thing. They give each other, they're just reciprocals of each other. Frequency goes up, wavelength goes down. So they're just inverted numbers, you know, one being the fraction of the other, so to speak. So if the wavelength is a positive, the frequency is a negative, and vice versa, a fraction. All right. So yeah, that's where it all starts and ends, I guess, for physics, is this idea of what is generating change. And if you think some kind of wavy thing is doing it, waves have to travel through mediums, generally speaking. So if you don't lock a wave to a medium, well, then you're kind of breaking the wave word. So I guess I'll just say wave versus, you know, versus medium versus what? Magic, right? Because there's no other way to do it, right? All right, without a medium for a wave to travel through, the concept of wave loses all of its relevancy. So clearly Tesla was a wave guy. Everything's waves because he believed in an ether. And so everything just became a push through the ether, through the vibrating mechanism. But it's still, it doesn't account for where the energy comes from in the jello itself. So for the jello to be doing something, for this medium to have energy in it conservationally, you have to imagine that the jello is a vibrating medium to start with, and that there's things coalescing out of that substance. I mean, matter, we know the E equals mc squared thing is that's like sort of rock solid. In the sense of the E equals m part of it. I mean, you don't even need the c squared. At least we don't know if that's even accurate anyway. You know, it depends on what they're going to use as an energy scale. So that's another thing wrong with physics. I mean, another broken element. Let me have a category of broken. You know, things they should have fixed a long time ago. The lack of a consistent scale to measure energy. Because, you know, they got calories and kelvins and joules and watts and, you know, lots of different ways of measuring the same thing, so a quantity of energy, a quantity of force. And so it just makes it you can't really do physics that way. I mean, physics is too strict in a sense. I mean, you can't, if you're going to attempt an accurate description of something, you can't change definitions midstream. You have to try to have consistent language. It's like if you're going to do a evolutionary tree, you can't have a mechanism that creates arbitrary or fake branching. It's got to be the real deal. You know, you just can't get away with this fake stuff. Yeah. So that's you know, if you're going to highlight the key mistakes in physics, okay, mistake number one is not understanding that, yeah, you've got to really be careful about this terminology. And then, you know, I would say that a part of the brokenness is that the mathematics lost connection also by using all these Latin symbols, and instead of having symbols that had explicit definition, you know, they'll just use something like theta or lambda. And the specific definition is, well, that could be the wavelength of the source. It could be the wavelength of the thing created at the end product. It could be the wavelength of anything. And then theta, the angle. It could be this angle. It could be that angle. It could be this angle. There's no obligation to explain whether it's a source angle or a product angle, a consequential angle, nothing. And so it makes the math so indecipherable just looking at it. Unless you learn their new language, which they've created, physics, their mathematical language, and when it means something, you know. So yeah, the language of the mathematics is just, it's a silly language. It's like, it's not more articulate. It doesn't have more definition in how it defines things. It literally is like going to something like an Asian Chinese language or something from English and saying you've made a step forward, when it's kind of obviously a limited language because it's just too symbolic. You know, you can't write it. You know, it's just very, you certainly can't type it, you know, practically. It's, you know, very difficult to turn it into something coherently converted into a written language. Yeah, so it would be better if there was acronyms or ways to say this is what we're talking about without converting to an entirely new language. Maybe even just having sometimes formulas written out in long language. I mean, yes, there'd be really, really long formulas, but exactly state what each unit is. You know, especially when you have 3 C's in an equation, you know, and then you put the little lower, you know, the little lower designators and stuff. I mean, it's bad enough the cubes things gets a little complicated, but I mean, the to the power thing. But you know, when they do that lowercase thing, sometimes it means something, sometimes it doesn't. Sometimes it means, oh, I'm just using the C variable again, so I'm just using, you know, the same variable. So this one's a different C, so I'll put a 1 by it because it's a different C. So anyway, it's just very, not very good equation language. All right. And so I'd say that bad equation language leads to lots of gimmicks, where you'd see the gimmick in the equation, where you'd see the, you know, where they've just multiplied the frequency times the wavelength to come up with a 0, because they're inverted numbers, you know, inverted proportions. You know, as one goes up, the other goes down, and vice versa. Okay, So it's just convenient. They use whatever one will blow up their equation in the way they need it to blow up, because it doesn't work in certain circumstances, so they need a trigger to blow it up. But that's a whole nother subject. But anyway, all right, so it's just not great language. Certainly not as clear as E equals M, energy equals mass. Or more specifically, mass equals energy. So, mass is a direct way to measure how many, say, let's call them electrons, are in something. And by measuring the electrons, you're measuring a certain constituent bit of matter that has to go with it if it's going to stay in one place, because electrons don't like each other. So if electrons are hanging out in the same ball of something, they're only doing it because there has to be a bunch of protons telling them it's okay, I'll make it work. You guys will find a compatible space with each other, because I'm going to organize you around me and you won't get in each other's shit. So see, electrons have a common spin. So let's say they're just all going clockwise. Two things going clockwise come into each other. Their faces are different, so to speak. So they'll always bang off of each other. They're spinning, because they're spinning the same way, they're spinning in a way that can't be compatible. If they get anywhere near each other, they bounce off of each other because their right sides and their left sides are not compatible. Their left side is going the opposite direction of the other guy's right side. And so they can't find any, that goes for top, bottom, all that other thing. So that's the giveaway, that we know that the element of repulsion between electrons is likely a symptom of that mechanism. The fact that spins are incompatible. Same spin is not compatible. Like tops, they'll bang off of each other excitedly. Even though that's not the actual mechanism, I just want to get to the point that it's you can sort of see that connection. All right, but I want to get back to the beginning, which is the particle thing. So if you there's conclusions you can draw, and you can say, well, look, am I going to be looking for elemental particle, or am I not looking for an elemental particle? Am I looking for something? Am I saying a force is something, or am I saying a force is something I can't understand, I can't know? It's something that happens. Things are just magically attracted and magically repulsed. But if I can see that, now it makes more sense that there's an actual mechanism. There has to be something that's pushing or pulling. So it has to be push or pull, but it has to be something pushing or pulling. I could say push or pull. And the important thing is something is pushing or pulling. So that would be a dividing line, a place where somebody can take a different road in physics in their understanding. Is they can say, well, am I going to accept that there has to be a something behind the force? The force has to be made of something. It isn't just isn't something that's nothing. It's something that's something. It's made of something. So there's some minor concession to that argument. 100 years from Einstein, they did start using words like virtual photon, which, yeah, it's just getting so close to the truth without conceding the truth, because they can't figure out where the photons would come from. So that's why they have to call them virtual, because they have to obey a conservation law. So they can describe the force of magnetism as virtual photons, being admitted perpendicular to acceleration, essentially, of the electrons. So wherever the electrons are moving, perpendicular to their movement, they're expelling these photons. And they call them virtual because they can't account for them. They can't say the electron's not getting lighter, it's not giving away something of its own, so to speak. But they can't go, you know, logically, their brain just isn't able to go back 15 steps and fix that first mistake where they did that silly wave thing and where they put gravity outside of E equals mc squared. Gravity's inside E equals mc squared. Gravity is a real thing. So gravity is the first force they ignored. They just made it go away. And ironically, it's it's kind of the first force. And that's where I guess you'd say the biggest mistake was made was, you know, Newton couldn't give you he couldn't tell you what it was. He could just tell you how it behaved. So that's what he did. And he said, look, I'm sorry, I can't tell you what gravity is because I don't know what it is. I don't know I don't know what it is, but I know how it works. I can give you an explanation for what it will do, this force of gravity. And then Einstein came along and gave this how, but the how, it was just an imaginary drawing of Newton's, well, the what, yeah. So let me, the what versus how. So Newton did how. Put that down. And then Einstein did what, but he did it just as a description of how. So he just created a gimmick, a way of metaphoring, okay, bent things, creating a depression in space, duplicates the curve of gravity, and it does so in this idea where if you metaphor it a certain way, you can say that the curve of that spiral is equal to a time that you can apply to what happens with the changing of the acceleration. So when something's changing acceleration, it's going to consume time to do that, and that extra time will be seen in the extra distance of that curved line. So he just came up with a visual mechanism, a structural mechanism that duplicates the inverse square law, and that's really all it's doing. It's just duplicating this. My hand's going to get 4 times bigger when I go half the distance. 4 times bigger, 4 times smaller. You know, true of light emissions, all emissions that come out in a straight line force. All straight line force emanations coming out in at spherical vectors, you know, will get you that. And that's how forces are admitted. So all forces obey this rule. Gravity, magnetism, electricity are all doing this. The closer you are to me, the more I'm going to affect you. Pretty much. Yeah. And that would change with things like laser beams. So the rule is, in a sense, broken there. You're not going to have the same diminishment because the beam, the admission of the force isn't in many vectors. It's all on one plane, so it's all coherent. So in coherent forces, coherent to each other, I don't know, parallel, probably a properly technical way to say that I'm not properly technically saying it that way. But anyway, yeah, so the rule is broken in circumstances, and not the rule, what fits in the category changes. You have to be a little bit careful. Not, you're not changing the speed of light, but you're changing how much the light is degraded, essentially. So obviously, an incandescent light bulb in space would be degraded a lot more in terms of its force on you than a laser pointer at the same position. The pointer has a lot better chance of getting its energy to you than the light bulb, for obvious reasons. I think obvious reasons. Anyway, but it's always a force, and it's always so going back to the problem. The problem is they took gravity and kind of put it in a separate dimension. So essentially Einstein created space-time, this fake place, this other dimension, and he shoved time and gravity, essentially, in that fake dimension. There's no such thing as space, right? We could sort of say that empty space, we could all maybe agree that that isn't a thing. So it's really this gravity and time he shoved in this fake dimension. So he took a function, which is time, and he took gravity, which is a force, and shoved them in a fake dimension, and therefore took them out of the mechanical sciences. And so that's essentially what the argument is you have to create virtual photons to explain magnetism and electricity, and even some of the nuclear forces. They use the term virtual photon. You have to create these virtual particles, let's call them that. Are particles that disappear, particles that do all kinds of weird stuff. So they even have now where they're popping in and out of dimensions inside of the atom to do this wormhole thing and this and that. And it's like, yeah, well, they have to do that because, again, they have to account for conservation. And they break conservation by creating something that can't exist. They can't create energy. They can't create matter. In a sense, they can't create, well, I mean, energy. They can't create energy. So I guess that's the right way to say it, because that's the energy makes matter. It's not matter makes energy. Matter contains energy. Energy makes matter. Energy is the thing you can't create or destroy. So the conservation rule obliges them, to virtualize, to make somehow not real the real carriers of the force. So it's the force carriers that they had to. The mechanism of a particle works. That's, I guess, the important part here. They're using virtual photons because the idea of a particle works. It explains the phenomenon, but they can't explain it that way because they can't make particles. Okay, because they don't have any source for the particles. Okay, particle works as explanation. All right. And that goes right back to 300 years ago, where particle diagrams of a particle, an active particle causing gravity. So having gravitons, having something, an invisible radiation. Let's call it that, an invisible radiation. So gravity is an invisible. If they would have started with that conclusion, okay, gravity is caused by an invisible, and I'll put that in quotes, so that's the key word, right? We can't detect it any other way than to be affected materially by it. Invisible, what did I call it? Damn, I forgot already. Invisible radiation. There we go. Okay, so that was Lesage gravity, or Lesage gravity, and it really is some guy in France, really some guy Lafrontier or Francesco or whatever, some guy who actually talked to Newton, and corresponded with him, and was supported by Newton in his concept, except they couldn't work out the thermodynamics of it. So when they made gravity a particle, the problem was then they were essentially creating an ether in the universe, and the ether would have a friction, would cause friction. Okay, so they'd have a friction problem. That's the problem with all ethers. I mean, none of these Tesla guys will explain to you how their mechanics of their universe is able to function without breaking this friction rule. I mean, how come it vibrates when you want it to, and it doesn't vibrate all the other times it's supposed to? I mean, logically would. When something's traveling through it. Like, again, how could you possibly maintain something like material velocity traveling through space? How could you move through space if space was an ether? Because you'd be constantly banging into the ether, and the ether would slow you down. You know, if you're claiming it to be made of something, something perturbatable. You know, and if it's full of this, it's full of the perturbation of gravity. So that would be the problem, is that if you have an active gravity, a particle gravity, then you're stuck with this problem. Well, what if, why when I fly into the gravity, doesn't the gravity affect me? And that's where that's where you have to do this kinetic thing. You have to realize that it's on the nuclear level, you know, on the subatomic level. It's all energy, it's all that same stuff, and that stuff is all acting kinetically, which it has the catch of being force neutral. Two kinetic balls in a frictionless environment are force neutral. They interact without any force being released, extra force. The whatever goes into the interaction comes out of the interaction. Nothing's theoretically changed. So that's another problem then. Okay, you say, well, nothing's theoretically changed. How does anything change? Well, the catch is that there's two other elements to how things can come at each other. So if I just made the whole universe of rocks, little marbles, just marbles, identical marbles, and we have these rules about how the marbles bang off of each other. And then, but clearly something has to be different. There has to be something else. And the difference is that, well, see, marbles probably aren't a great example because, yes, it's better to have the Frisbee example. So I just make the entire universe out of Frisbees. Now you can understand the first element that goes with this thing is that all the Frisbees have a polarization. They have an angle they're flying at you, coming at you. They're coming at you flat, they're coming at you on end. So they have a plane. Okay, like a galaxy, photons are traveling on a plane. They have a diskness to them that it allows them to express polarization. And now the interactions have rules. What happens when two Frisbees of opposite polarization interact? Well, this would be opposite retard. Speaking to myself. What happens to the interaction? So at these different polarizations, there's different rules for what is exchanged. Does this polarization come out this side, or does this polarization, do they convert their polarization? So the two things, let's say they came directly into each other, two Frisbees. The real question is going to be, is it going to be a bounce off? And then if we see it as a bounce off, like two kinetic balls, they just bounce right off of each other, same force going out as coming in. Do they carry their polarization, or does this happen? Does this polarization go this way and that polarization go this way? Or do they actually convert the polarization in the sense that the polarization changes direction? So that would be important. If the polarization is actually changing direction, then that's a change. Okay, so well, anyway, so the key thing is there's only these two things. There's polarization, which you can understand that can cause change. And then there's, let's see, cause change. So speed and momentum can't cause anything. They're all going the speed of light, all the frisbees. And again, all the momentum will be exactly the same after the interaction as before the interaction. Two things go in, two things leave exactly the same direction they would have gone if they never hit each other, which is bizarre, but that's what happens. The thing that changes is their polarization changes. The polarization doesn't travel through the interaction, it bounces off. All right, so the other thing they have is what could be called frequency, wavelength. So now this, oh, the wave thing showed up, right? But it's not really a wave. You know, me doing this, okay, that's not waving, okay? That frequency of interaction, it's not reasonably understood as a wave. Water dripping into a puddle. The water going towards the puddle, the droplets, are not waving. You don't say, hey, there's a wave of water. So let's understand that it's a frequency that's causing that. And that's all. So now understand the frisbees are flying and that they have a polarization. Now, if you say you had a row of 10 of them and every third one was polarized the same way, okay, so you have a row of 10 frisbees coming and every third one is polarized the same direction, you know, it has the same plane, and the distance is the same between one and the next, then you could sort of understand that that row has built into it something we can detect as light, because now it has a frequency. It's carrying, it can be detected because the polarization is the same and the distance between the polarization is the same. And so that's what really a ray of light is. So all rays of light, let's understand the difference. When light's created, it's created by electrons. And it can spew electrons from one location, you know, one orientation. So if the electrons are all aligned the same way in the matter, or generally a lot of them have the same alignment, then you'll end up with a kind of coherent light, you know, a bunch of rays coming from the same direction. And then if they have the same polarization, that can also take place. But that's sort of the catch is each ray is a consistent polarization. And if the matter usually would have electrons in all kinds of different arrangements, so then each ray, and that's why the elements have different color bands in them, is because of the polarization, essentially, the strength of the polarization at different angles. So each ray of light will have its own polarization. It'll be like a row of them that are all the same. So what I'm saying is the ray of light ends when the polarization changes. So if the polarization changes, that ray ends in a sense, but it can't be detected by an electron. The electrons can only absorb polarization within specific orientation. You know, so specific angle is acceptable to an electron. That's it. It can't accept anything else, and that might be a very narrow. I mean, I did this, but it's probably really rigid in the sense that you got to come in. It's like galaxies are kind of flat in space, and you could sort of understand that if something's going to come into that galaxy and be absorbed, it has to do it in this flat part. So it has to come into the flat side of the, you know, coming up this way, it's likely to go straight through, not hit anything. A lot bigger chance of hitting something if it comes in from the side. And electrons have a similar mechanism where light's got to come in the right way. Ken again, damn it. I told you to go away, didn't I? I don't know how you got. I don't know how you came back. I mean, I did block you, didn't I? Well, why would I use another word than polarization? It's a brilliant word. I mean, this explains it. It has a top and a bottom. I mean, polarization is basically saying you have a top and a bottom. You know, geometrically, spatially, you have a top and a bottom. It matters. There are many. Are there any? Synonyms would be. Oh, let's see. Well, yeah. I mean, orientation. I mean, orientation doesn't sound better than polarization, does it? But I mean, it's an orientation in space. I don't know how to. You got 360 degrees plus the other 360 degrees. This. I mean, there's, you know, the angular polarization. You know, when you take into account which vector it's flying at, you know, it gets, you know, impossibly complex when you combine those two things. The direction of your which way you're moving and which way you're polarized. What happened in dark with no light? Jeez. Obviously, nothing happens in dark with no light. There's no light. There's no polarized gravity coming at you. So you can't see the gravity, but the gravity's still there. For the sake of covering all bases and removing all ambiguity, essentially light is a concert is basically just converting gravity, the force that already exists, into something visible by giving it frequency. So you can kind of understand that only electrons can receive frequency of polarization, and only electrons can expel it. Let's make that the rule. And then you can sort of understand that they're just they're just taking the regular force that's always coming in, the gravitons, and they're just converting some of the gravitons into what we call photons. But again, the word photon doesn't work in the sense that if you understand it as a particle, you wouldn't say photon, because you know that two of them are required for an electron to absorb it. It has to have the balancing element. It has to have both polarizations, so to speak. It has to have a, well, I don't want to say that. It doesn't want anything to do with both polarizations. But I just mean that you can sort of understand that anything to get captured, there needs to be a balance in the weight. So there has to be, if one's coming in the top, something has to weight the bottom. So there always has to be conservation to hold matter together. So an electron can't hold a new piece unless it comes in pairs. That's one of the rules. So we'll just write that down as a rule. The rule is, you know, consumption requires a pair. And it still doesn't mean that you're going to be able to hold it. It just means that you'll have a chance. You have no chance without the balance. Well, look, you can say it, all right? You can say something's dead. Yeah, it's dead as meteorites, okay? It was not, they didn't understand, they never saw the steel balls bouncing off each other. Well, you can see that. I don't think they had invented those things yet. But do you understand kinetics? Do you understand that in the kinetic universe, there's no friction? Nothing breaks apart. You can't understand an indestructible particle that can't go anything else but one speed, okay, and can't break into pieces. You can't understand that. Because to say Lesage gravity is dead is to say you can't understand that. Feynman couldn't understand that because he metaphored Lesage gravity to raindrops, for fuck's sake. He's a fucking physicist, and he compared. This is the guy who used the term virtual photon. You do know that, right? That Richard Feynman used the term virtual photon to describe the force of magnetism. Do you know that, cunt? Jackass. The only thing dead is your goddamn brain and your goddamn imagination. The fact that you lack imagination should have you sitting in a corner shutting the fuck up, because you can't think. You have nothing to base your your declarations. God says so. The sage gravity is dead because you say so. Or the Pope said so. The Pope says evolution is wrong. That's how you sound, fuckhead. You don't have an argument. And again, it's a 300-year-old theory, fuckhead. Well, almost. It's older, by a few weeks than Newton. Okay. I don't even know what that means. Elemotion A? I don't know what that is. A little blurry. It's morning. Elemention? What is that? I have no idea what that. I don't know. I can't say it any clearer, right? If I have a big pile of galaxies, and some of the galaxies are this way, some of the galaxies are this way, some of the galaxies are this way, I put them in a string, okay? And some are just pointed the wrong way, right? So just think of it as, think of the way the thing is situated as color, right? So this would be the color red. This would be the color blue, okay? So think of those as the two extremes. And the point is, if you had a row of beads coming, a row of them, you could have lots of reds, but the only ones that matter really are the ones that are blue and they're at the exact same distance from each other. That would be called electromagnetic radiation. The same frequency and the same polarization equal electromagnetic radiation. If it just has polarization, then it's magnetism. If it has polarization and a frequency, then it's a real photon, not just a virtual photon. So you could say when they don't have frequency, they just have polarization, then they're virtual photons by Feynman's definition. And when they do have frequency, then they're photons that you can see because electrons can absorb them and be moved, which causes the reaction that we call, I saw that. That's how your eyes work. You vote for Donald Trump like I do? Well, you're on the wrong subject, retard. So I guess you'll have to go away. I guess you will. Retard. I mean, what the fuck you doing in here with that crap? You can't figure out, I really don't want that subject in this room. You can't figure that out all by yourself. Jesus. Dumb fuckers on this earth. Well, then it's redundant. Elemention is elementon. Okay, now I see what you're saying. You're saying elementon. Okay, so we have to come up with some other way to write elementon. You're kind of putting the hyphen in the wrong place, right? It would be elementon. The ton part needs the dash. Okay, so you gotta get that right. It's a ton. You can't go elementon. That doesn't make any sense. So capitalize the T or something. Yes, so all you have is, look, if you call them gravitons, that works too, magneton, but I'm just saying, so let's just call it an elementon, and the simple rule is, okay, when it's not of the same polarization and it has no frequency, we call it gravity. Okay, when it has polarization, that means it's all coming at the same polarization, we call it electromagnetic force. And if it's both polarized and comes at a frequency, then we call it light. So polarization plus frequency equals light. Polarization alone equals electromagnetic force. And neither polarization or the same frequency equals gravity. So anyway, that's the point I wanted to get to with this whole explanation, is that that's how simple it is. But you have to sort of explain why they didn't see how simple it was, right? And the reason why they didn't see how simple it was is because assholes, whites, fucking cunt, jackass, you know, yeah, I just want to use every kind of nasty word. Fuckers like that stupid logical empiricist. The assholes like that were around. And, you know, because they couldn't figure out how to do something in 20 minutes, they gave up. And giving up on a particle explanation of reality was a huge mistake. Catastrophic to physics. Wave theory is babble. They should have been able to say to themselves, look, all right, we can't make particles work, but waves don't work either. So let's just give up on, come on, let's just not declare waves the winner when it just doesn't work. You can't even imagine how this wave goes 15 billion miles through space and it doesn't spread or do anything till all of a sudden it finds a double slit and then it does all kinds of shit. I mean, it's just so stupid. But that's it. That's the mistake. Because once you do particleize it, you can see that all you do is have a subtle feature of the particles, a subtle difference in the particles, and now in the rules of their behavior, in the sense that they'll not exchange polarization, which means polarization reflects off interaction. There's your room for change in the universe. The polarization doesn't travel through the kinetic interaction. So the blue thing hits the red thing, and the red thing doesn't continue on its path. The red thing goes blue, and the blue thing goes red. And there's your change in the universe. And of course, the frequency thing, which becomes only is made possible because now you've you've created this opportunity. Well, it's that no. The frequency is made possible by the concept of the balanced orbit, the dumbbell, the idea of the spinning dumbbell. That there has to be two things being blocking force on each other. They get trapped in the arrangement, the force of gravity. So gravity forces things into association with each other, and that association, which is a spiral usually, creates frequency. It has a rotation speed, and so things will leave it at consistent speeds. I mean, consistent time intervals because of the spin. The spin is a time interval, and it creates the potential to release things at a frequency. All right, so that's not too bad. It does get a bit exhausting going through the whole sloppy mess. But yeah, I always have to do that in a show kind of manner because I see that it's all about the show with people. You know, I saw a physics video on Maxwell's equations, and you know, it was done very well. You know, they're just sort of the simple arguments about the perpendicular forces and all that kind of stuff, and you know, and through this new vision of mine, you know, once you understand what's really happening, you can just see why the thing is doing what it's doing, because you can understand that as soon as you accelerate the charge has to release its perpendicular dimension because it's going the wrong way. So it has to get rid of, if you're going to accelerate me, you got to get rid of the bits that aren't going the right way. Simple as that. There's little pieces of me going the wrong way. Well, those little pieces got to get the fuck off the boat because I need pieces going this new way. And you can just see that happening. But the funny thing was, it was done with like a video game software, you know, and so it was just, it had a bunch of chicks, you know, holding little round, you know, charges, and you know, it was very cleverly done, animations and stuff, but it's just like, it was just so bizarre, you know, because it was like, you know, a bunch of animated game graphic chicks, you know, conducting the experiment, so to speak, with the little round things. But yeah, it was all particles except for the force, which is the funny part, right? So everything was some sort of round little particle except for the force. That wasn't a particle. You know, and I was just saying to myself, well, if you just turn that, if you just take your little round thing and you just expel little round things from it as the force, you'll have a much better illustration of what's taking place. And if you understand that all the round things have to obey the flow of that force created, the flow of the force essentially becomes a kind of ether in the sense that it becomes a tsunami of some kind. It becomes this increase in the volume of relevant stuff coming at you. So, if I'm only affected by blue, and gravity's hitting me with red and blue in equal proportions, then it's neutral. But as soon as it increases the amount of blue coming from one area, you could sort of understand I'm sensitive to blue. Blue gives me sunburn. All of a sudden, I'm going to get burned. There's an effect that's going to have by simply converting the color, by simply changing the polarization. You change the magnitude of the force as it affects an electrons, depending on how my electrons are lined up, of course, to be blue sensitive or red sensitive. Anyway, I didn't do a brilliant job of explaining that. I guess, that's critical to this whole explanation, is just getting to that. It's okay to visualize forces as actual things leaving something, and then they go somewhere and they affect something. So the idea of a virtual photon, if you just call it a real one, and just say, look, imagine the force as light emanating. And then just say, look, a magnet basically is this side of the magnet, the north side. Where'd my video thingy go? Let me open that. It's gone. I can't see whether you're seeing this. All right, so the top part of the magnet would be, the north and the south. That's sensitive to the red polarization, and then you go and the bottom is sensitive to the blue. And inversely, the top part doesn't see blue at all, and the bottom part doesn't see red at all. It goes right through it. Doesn't even affect it. So, and then you can sort of understand that if I turn these lights on, of these two magnets, now I turn the light on, I actually emanate from this one, depending on how much magnet it has to go through. So depending on the thickness of the magnet will dictate the polarization. I mean the amount of strength of the force of the redness. How red it is or how blue it is depends on how long the line is to get through it. So you can just see that if I put two magnets together, that this side's going to be lining up exactly with this side, in the sense that they're, if I both have them north facing, then this one's going to be producing something that's invisible to this one. I mean, visible to this one, that it's sensitive to. And this side's going to produce something that's this one's sensitive to. And so they're going to end up being pushed apart because this is the double sensitive. And likewise at the bottom. And then if I invert the magnets, you can see that the thing is, now the two things they're creating is exactly the opposite. This magnet's creating the thing that this thing doesn't see at all, and this one down here is creating the thing that this one doesn't see at all. And now gravity will smash them together hard and fast, because now gravity is a stronger force, because you took part of the gravity away by turning it into an inert thing called the wrong color. The polarization is invisible to the matter. So essentially, a magnet is making the magnet invisible to one spectrum of gravity. But the key is it's doing it proportionally. So the one spectrum it's invisible to, it made another spectrum twice as strong. So now it doesn't get changed in regular gravity. That's why these magnets don't fall faster or don't move don't do anything. I mean, they're gravitationally neutral because the north side is twice as strong and the south side is twice as strong in opposite polarizations, and they're invisible to one spectrum. So it's 2 plus 0 equals 2, 1 plus 1 equals 2. So the conservation of the gravity is maintained. Anyway. Yeah. All right, and then electricity is the. I mean, look at the fact that it explains all this stuff. It's just so obvious. This is the answer. But the evacuation of essentially electrons from a wire through this magnetic force. This force goes into the wire. The if you thought of it as a light being turned on, and any electrons, it's going to go into those electrons, the force, and if they can absorb them, they're going to gain an acceleration from the absorbing this force, this extra gravity, essentially, that's being thrown at them, because they'll see it as gravity. If it's an off polarization, they just see it as gravity, in a sense. Well, it's not the right way to say it. Yeah, no, it's not the right way to say it. They're only going to be if it's on their polarization, it's a double force. If it's off their polarization, it's invisible. So I guess that's the important thing to say. It's just that if it misses them, it misses them. And it's likely to miss them when it's going the wrong way, when it comes into the galaxy the wrong way. So when it comes in to the galaxy this way, it's going to look pretty invisible. If it comes in this way through the thick part, it's going to look pretty visible. So the force is coming at the right angle of the galaxy. So it will be pushed, and it'll be pushed in this cone kind of spread out kind of way. So the electrons in a wire, when the force comes at it, what it's essentially doing is the ones that are forward are getting hit from behind completely. So they get pushed in those two directions. And once they move out of the way, the other electrons now have more space, and so they will occupy more space. So they will accelerate because they have less force confining them from the other electrons. So they'll also spread out. And the problem is, though, is that once you do that in a wire, the reason why you have to keep turning the magnetic field on and off is because the flow can't change now. It can't do anything. Once you've cleared the wire, there's no room to create acceleration. So you can't create any voltage. Electrons already moving, already accelerating, can still go through because they don't have a tangential dimension. Their galaxy has gotten really small, really thin, let's say. So it's really hard to hit. So one moving is very hard to hit. And what's the word I'm looking for? Well, anyway, but you can just get the idea that the reason why it has to be, you have to turn the field on and off, is because you have to keep letting the electrons back in and then pushing them back out and then pushing them back in and then pushing them back out. And that's the key to the whole thing. It's a clearing force, and once you've cleared them, it's like say everything was, the light from the light bulb was repulsive and pushed me away. You'd have to turn the light bulb off for me to go back to my normal position. So I get pushed away and then I come back. So the only way I can come back is the light bulb has to turn off. So you have to turn it off. You have to turn the field on and off to create electricity. So if you leave the field on, it's just blocked. I mean, the wire's blocked. It's blocked from initiating voltage. It's like I said, an existing voltage will still travel through the wire. Well, that's what limited. I gotta do some research on that one. It certainly won't keep flowing through a transformer. So, I'll have to come up with. I mean, you can't like run a voltage. I mean, if you put voltage into both the secondary and the primary of a transformer, you're going to get a real problem. So yeah, there's no, there's no pre-existing voltage. You really can't have a pre-existing voltage in a transformer. So theoretically, that probably goes true for a bare wire. That if it wasn't for the fact that the bare wire has no coils and that you're affecting it so little, that must be the only reason why a magnet doesn't fuck up every electronic device entirely. I mean, something about that not having enough of a it's the whole square inches of travel distance is what makes all of this thing work. So the reason why a magnet doesn't affect, like I said, an iPod or something, if I put a magnet next to the computer, it's not going to stop working. Is that there's, unless I put the magnet near a coil. So if I put the magnet near a coiled, one of the little inductors, or what do they call the little transformers used to make frequencies? So you got capacitors, you got resistors, inductors, right? Yeah, inductor. So if I put a magnet next to an inductor, I will fuck the computer up. I mean, I will change the frequency of something or whatever. I will probably mess up the function of the motherboard. Probably. I think you'd have to. Yeah, I just don't think there's a way to avoid that. I don't think. Yeah, I have to think on that one. Because it's still the magnetic field has to be introduced in the right plane of the inductor. So you might have to put the magnet next to the inductor, not over the inductor. Maybe I'll try it. Yeah, well, a superconductor just means that the electrons are lined up for maximum efficiency, right? So, so you could argue that one electron has a potential to carry a certain number of photons in a direction, and it's just that it can achieve its maximum speed of exchanging packets of electrons. So let's say there was a million photons in an electron, and I move an electron from point A to point B. I've moved a million of these little gravitony things. So the more efficient that transfer is, so the less funky lines it travels and the less bullshit it goes through, the more efficient that's going to be. But that's all a superconductor really is. It's just a really efficient transfer of the force into electrons, the movement of electrons, and then the electrons move very efficiently, carrying these packets of the force, and then convert the force back into a force again, whatever that force may be. So it just makes it a very, very efficient at carrying electrons. Yeah, well, it doesn't really. I mean, it's not like you can get something for nothing. So the force going into the conductor is still going to be basically this gravity thing that's going to create any kind of internal currents in the matter. So until you start breaking the matter, you still can't release any real energy. I mean, a superconductor isn't creating energy. It's revealing energy that already exists. Well, yeah, I don't know much about high temperature conductors. I mean, you can just surmise that the two elements of high temperature and low temperature would have a certain advantage in that you have to keep things simple, right? So anything that's complicated is not going to. Medium temperature is just medium velocity, in a sense. So that's where things can get messy, because you have velocities in different directions. And you can sort of understand that at very high temperatures, you have a tremendous amount of force going in probably one direction of the, wherever the source of the heat is. It's pretty hard to create like a perfect, a plasma or something. But if you did, that's still a force all the way around something, you know what I mean? So it only has nowhere to go, so to speak. So the superconductors at high temperature are likely being contained in a container. And that container is essentially just creating a very good path in the middle, because the matter is less dense in a sense, right? I mean, if you're heating something you've got a lot of movement in the particles, and a lot of movement means that you're releasing a lot of tangential force. And you can sort of see that would create some necessity to have very strict alignment, because if you have a lot of stuff moving, matter, obviously it starts to fall apart unless it's very efficient, right? I mean, that's probably the best way to put it. The more complex the matter, the harder it is for it to retain its form when heated. So the more complicated I make the arrangement of the atoms, the less tolerable to heat it's going to be. So anything at a high temperature would be something fairly efficient in terms of it have to be a crystal or ceramic or something that where the alignment of everything is very strict, and so it's very stable. And anything stable would be a good conductor, theoretically. Yeah, I think that'll do as an explanation. I think so. All right, so what else? Yeah, so anyway, I was thinking on the Maxwell thing. This is always that's why I was just thinking about the curved part. Because there's this whole part that almost implies, once you've accelerated a charge, it does take this little period of time for the effect to reach the thing it's going to. It takes time. And then when it reaches that thing, it causes acceleration, which causes the thing to release force back. And that's the whole inductive part of it. And, that these forces induce reactions in each other, and then there's a time delay. So the induction really has to do with the limits on speed, the speed limit. Is the cause of that feedback loop. And so you really, to get to, and I guess the feedback loop is just kind of like almost like an audio feedback loop, it has to accelerate to its maximum point. And then when it gets to its maximum point, it just does this obnoxious superconductor thing. It just makes a horrid sound and, maxes out in terms of its capacity to absorb energy. Something like that. But then that gets to the whole limits on when the oscillation or the period of the frequency, the period of the feedback loop. All right, period of feedback loop. And the fact that things are frequency sensitive. There's a frequency that once you exceed the frequency, everything breaks down. So I think it's called a breakdown frequency. But it's kind of like the breakdown voltage, for charge. The atmosphere has a breakdown voltage of whatever, 3 million volts or something. And per inch or whatever. So once you have an inch of space and 3 million volts, you'll have the atmosphere is going to eat that space. I mean, the voltage will jump that space. And so anything smaller space has a lower breakdown voltage. But then a further distance has a higher voltage. But that's the kind of funny thing, is that there is no, they say there's no monopoles in magnetism, but there really are no monopoles in electricity either. I mean, all charge is essentially a relativistic thing. I mean, it's and all. So you could just argue that everything's a pole relative to whatever the ground field is, so whatever the strongest field local is. But there's always a field of the biggest field, so you always have a charge imbalance somewhere, because that's what's creating the whole. Like I said, the charge is just an expression of this fact that polarization can be collected in a sense, that it can be stripped from its origin, graviton, and sent back where it came from, causing, excess polarization. More of one polarization. So depending on what you're bouncing back, it's a filter essentially. Polarization can be filtered. I guess that's what I wanted to say. Well, look, I would argue that bunk is a tricky word, but I'm saying that, look, atom smashers that create particles that last for 5 seconds, that might mean something. Okay, if the particle, the thing, lasted 5 seconds. These things don't last any time at all. They are not real things in the universe. They have no durability. They're pieces of things. And the pieces obviously get reabsorbed by the matter around them because they're going to move wherever the force is moving. So wherever the force is going, they're going to go. They're going to be charged inevitably, in a sense, charge sensitive. But I mean, yeah, you want me to say that it's bunk to call something a fundamental structure, a fundamental element of atoms that has no survivability outside of the atom? Oh, well, that might be possible, but I don't think that makes sense in terms of making matter. I don't know how you could possibly make matter that way. So I guess I would just argue that certainly I think the idea of creating a gravity particle or a mass particle is silly, because obviously that's not how it's working. I mean, all of the particles are equal. There's no particle that has the mass of the atom. It's creating its atomic weight or any of it. No, it's just not. They're all part of the conservation of energy. They all have energy. So yeah, I don't know what what do you want me to say? I mean, the evidence for the Higgs boson is all basically theoretical, and a tiny bit of, they didn't actually find a Higgs, right? They found something they say Higgs turn into, because Higgs last so little time, they instantly convert into a bing bong bong, and so they found a bing bong bong, and they say, okay, well, we got a big bing bong bong, that means there must be a Higgs. That's how weak the evidence is. So you want to live and die by, the evidence produced by atomic accelerators that smash things into each other? You want to learn how Volkswagens work by smashing Volkswagens into Volkswagens? Be my guest. I rather carefully and methodically take them apart. And I don't see any point in smashing things to say I'm going to figure out what it's made out of. Applying a big pile of force, E equals mc squared. Again, matter is energy. You're saying I'm going to figure out how matter works by shoving a bunch of energy into it. What these people, these retards who don't even speak the goddamn language, coming into rooms? Who are you? What the fuck are you doing here, retard?
Cállate.
Yeah, well, baby. I mean, yeah, it just makes you say, gee, Trump is the dumbest piece of turd in the universe. But yeah, he's smart enough to say these assholes ain't going to make America great. Just a bunch of baby-making Catholic kookballs. We don't need no Catholics. We don't need no Muslims. That ought to be the rule. You want to get into this country and you're Catholic or a Muslim, then yeah, retarded Mexican fucker. once, I kick you again, okay? Yeah, it's okay. I kick you again, retard. God. I just nuke fucking Mexico. I mean, Jesus Christ. How can you be so fucking obnoxious? I mean, I just can't, like I said, I can't imagine. I go to China. Or I go to a Chinese website right now as an American, and I go into a Chinese website and do this and feel what? Proud of, hey, I'm showing the Chinese how great America is by being an obnoxious asshole. Ooh, habla asshole, habla asshole, habla asshole. I don't know why they don't give you a better feature here. I mean, how do I block this fucker? Should be a way to do that. Let's see. I guess they have to get into the chat. So a list of available commands. I don't want available commands. I just want to be able to block fuckers. I guess I have to wait for him to show up again. I don't know. I gotta click his name real quick and block him, I guess. Death made me drink my coffee badly. Killed by Mexican. Fucktards. Anyway, where was I? Before that, whatever that was. The people, yeah, just, oh God. So, yes, so yeah, I don't think there's any gravity particles inside atoms or any particle that's holding everything together. Clearly, I think there could be a mechanism, between protons and electrons. Obviously, protons don't consume electrons. So there's obviously, I think, a mechanism, a membrane between the two. But I think that's probably the neutron, actually, but it doesn't really matter. But it's only because of the Standard Model and their creation of all these bits that they have to create the idea of a Higgs boson. So I'm just saying that's their creation, because they don't understand what gravity is. They don't understand that gravity becomes magnetism. So they can't really understand how this thing really works. So they have to create these fake particles that jump around from player to player and give them mass all of a sudden. It's like dark energy or dark matter. It's a way of making the math work, but it's not. I mean, if you really think about what they're saying, is this, this Higgs bounces into everything and causes everything to get, to have gravity for a second, and then it goes away, and then it has gravity for a second, then it goes away, and then it has, it's really complicated in terms of its function. So yeah, I don't think it's a real thing. I wouldn't bet on it, I guess is all I'm saying. I mean, so if you're if you're in the jury and you know that if you give the right answer, you're going to get a cupcake, and if you give a wrong answer, you're going to get a nail in your eye. Aren't you going to say, I'd rather not answer on the Higgs? I mean, are you willing to say you're sure they exist? Oh yeah, I'm quite confident they've got that nailed just right. Yeah, I don't think so. So, I mean, when you have nothing to lose, it's really easy to invest in that kind of mush. I would, okay, I am quite confident that, yeah, the answer is it's all one force. Gravity, magnetism, electricity, it's all one thing. It's just being a different expression of the same thing. That's why they all travel the speed of light. So the entire electromagnetic spectrum, all radiation, and all force are all the same thing. It's just some is visible and some is invisible. But what more data do I want on the photon? I don't understand. All I'm going to do is find out how much one weighs by Einstein's math. And then I'll be able to have a realistic, I mean, I just want to get the photon to electron ratio right. Right, because they already have the electron to the proton. Right, I can't remember what it is, but it's like a, yeah, I don't even remember. I mean, they say a neutron is just one proton and one electron, right? I mean, it's not much. But anyway, which doesn't make much sense. But anyway, what I need is I need the atomic weight kind of idea. So I got to find the atomic weight of electrons and photons. And so once I can give everything a proportional weight, then I can really do something with this nonsense. But you can understand the effect of a force, the photon. So if I took something that was made of 10 photons, and they're going up and down, forward, back, all that kind of stuff, and I introduce a new one into that field, into that piece of matter, going in a direction, well, you know that the speed of light's the critical thing it's doing. So it's introducing the speed of light in a direction, and that has to be proportionally balanced against all the other stuff that it's doing. So you can kind of do the math kind of simply and understand that whatever the density is of the mass, any piece of mass has so many photons in it. But you can just see that one photon, it's the speed of light divided into the atomic weight of the thing the speed of light just joined. So it's dividing a huge number into a huge number. And that'll tell you how much acceleration you'll give the body, essentially. So that's what I got to work on. Jeez, quite rude. Yeah, people, just so hateable. I mean, maybe he did it by mistake or something, but it doesn't matter. Too stupid. I don't take it personally, Ken. I just don't have time to waste. You know what I'm saying? I really don't. And, I sincerely say, okay, I'll read your shit. I try to figure out what you're saying. You don't understand how my time is. I can't tell you how I know it doesn't look like time is precious to me, but it is. Okay? And I have to use this. I have to waste a certain amount of time just being alive because being alive sucks. So there's a certain amount of waste that's inevitable. And I'm just saying, when somebody's increasing the amount of waste, That's going to get you, you know, you're pissing me off, fucker. I mean, you're really not helping. So, fuck off. I don't know what that means. I don't even want to think about what that means. Cow queers? Why do I want to waste my time on that? Why do I want my brain wasting its time trying to figure out what the fuck you're talking about? Damn. There really is no hope for this planet. So few brains actually work. Consistently, reliably, dependably, usefully. So I don't know if there's anything else to bibble about. Maybe I'll head off and get busy with my chores for the day. And such. So I don't think there's anybody else here worthy of my worthiness. Yeah, bothering with. So anyway, the trolls addicted to cow breast milk. Yeah, whatever. Whatever. Yeah, call you a troll calling trolls troll. It just doesn't make much sense. Trolls trolling trolls or whatever. Fuck. Too many fucking idiots on this planet that don't know they're idiots. Have no, idiot discipline. It's like everybody just walking around. It's like, if I had some kind of farting disorder, and I just constantly was making a stink and farting and stuff, I would know. Oh yeah, well, restaurants are out of the question. It's just that people have no discipline. They can't control their whatever it is. They're just such assholes. I mean, fuck, not to know their limitations. It's like so they're like little obnoxious little kids who've been told how wonderful they are their whole life, and so they think they can just walk on to like a professional baseball field and play with the professionals. They're just like that kind of obnoxious kid. Yeah, I want to play. Yeah, I'm entitled. Yeah, well, I don't think you're doing it, Ken. I think you're a ton of shots behind. But whatever. Go ahead, aggrandize yourself. Yes, you're 100 moves ahead. Yeah, sure you are. Anyway, fuck. Yeah, right there. Some asshole thinks he's 100 moves ahead. Right there. You're just like, yeah, what assholes? So somebody's not humble enough to say, I don't got clue one ahead. I can barely, understand what just happened, let alone understand what's going to happen. Anyway, till next time and such, so forth and whatnot. Blah, 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 blah.